Acid-base disorders are common. They range from minor to life-threatening. So, knowing how to diagnose and treat them is critical. When thinking about acid-base disorders, one of the most useful places to start is with the Henderson Hasselbalch equation, which is routinely used to measure plasma pH. The Henderson Hasselbalch equation states that the plasma pH is equal to 6.1, which is the dissociation constant of carbonic acid, plus the log of the plasma bicarbonate concentration, divided by the partial pressure of arterial carbon dioxide times its solubility in blood, which is 0.03. The Henderson-Hasselbalch equation was derived from this basic equation, where the pH is equal to the pKa, or dissociation constant of the weak acid. In this case, it's carbonic acid, plus the log of the conjugate base, in this case, bicarbonate. If you recall, carbonic acid is produced when carbon dioxide is dissolved in water. In our case, it's dissolved in blood. Normally, this reaction is slow, which is why it requires the enzyme carbonic anhydrase. Once carbonic acid is formed, it spontaneously dissociates into bicarbonate and hydrogen ions. Now, for a number of reasons, which we won't discuss at this time, it's more convenient to measure the partial pressure of carbon dioxide than it is to measure the concentration of carbonic acid. So having said that, let's use the Henderson-Hasselbalch equation to estimate the plasma pH. We'll use the normal plasma bicarbonate concentration of 24 millimoles per liter and a normal partial pressure of carbon dioxide of 40 millimeters of mercury. Doing so yields a normal plasma pH of 7.4. Let's finish up with these important takeaways about the Henderson-Hasselbalch equation. First, the equation shows that pH directly varies with the plasma bicarbonate and inversely varies with partial pressure of CO2. This means that changes in pH, which are due to variations in plasma bicarbonate or partial pressure of CO2, can be corrected by changing the other variable. For example, if the bicarbonate concentration decreases, it will lead to a decrease in plasma pH. So, to correct the plasma pH, a decrease in the partial pressure of CO2 is required. On the other hand, if the partial pressure of CO2 increases, an increase in bicarbonate is required to compensate or correct the pH. Second, the equation provides a simplified view of how pH is regulated. For example, plasma bicarbonate concentration is primarily regulated by the kidneys, while the partial pressure of CO2 is mainly regulated by the respiratory system. With this in mind, we now have a framework for diagnosing acid-base disturbances. For example, the bicarbonate concentration can be affected by ingestion of acids or bases, increased production of acids or bases, the increased loss of bases in the stool or urine, and the decreased excretion of acid in the urine. On the other hand, the partial pressure of CO2 is affected by changes in the production of volatile acids, pulmonary ventilation, and/or composition of the inspired air. In simpler terms, reduced bicarbonate concentration is associated with metabolic acidosis. Increased bicarbonate concentration is associated with metabolic alkalosis. Increased partial pressure of CO2 is associated with respiratory acidosis. And finally, decreased partial pressure of CO2 is associated with respiratory alkalosis.